Hello, everybody. Good evening to all. Welcome to our International Physics webinar. Today it's our 281st International Physics webinar. And today we have with us Dr. Professor Jacob B. Simon, and he's currently working as an assistant professor, Department of Physics and Astronomy, Iowa State University, USA, and he's also already connected with us. So I'd like to welcome our speaker. Sir, good morning to your part and good evening to here. Thanks for joining with us. And it's our honor and privilege to host you, sir. So before going to you, I'd like to introduce you with our student and viewers. So I think dear student and viewers, I think you have already come to know the title of this today's International Physics webinar, and the title is the Planetesimal Formation in Circumstellar Disk. And our speaker is Professor Jacob B. Simon, Iowa State University, USA. And he has completed his bachelor degree from the University of Illinois Champaign-Urbana in 2004, and his master's degree in astronomy from the University of Virginia in 2006, and his PhD in astrophysics from the University of Virginia in 2010. You can see his research interests: planetary disks, planetary science, exoplanet, compact object, computational astrophysics. He started his research career as an undergraduate research assistant at the University of Illinois in 2000, and he stayed there up to 2004. Then he joined as a graduate research assistant at the University of Virginia in 2004. He stayed there up to 2008. Then he joined as a NESSF graduate research fellow at the same university, University of Virginia in 2008, and he stayed there up to 2010. Then he joined as a JILA postdoc research fellow in 2010, and he stayed there up to 2013. And in 2013, he joined as a NASA second fellow, Southeast Research Institute in 2013, and he stayed there up to 2016. In 2016, he actually joined as a senior research associate at the University of Colorado, and also a visiting scientist at Southeast Research Institute. And he stayed there up to 2019. And from 2019 to still date, he has been working as an assistant professor from the Department of Physics and Astronomy, Iowa State University, USA. He got a lot of awards and honors from different organizations, and some of them we can see: NASA Sagan Fellowship in 2013, NASA Earth and Space Science Fellowship 2008, Virginia Space Grant Consortium Fellowship in 2008, and also he got some research grant from NASA and other institutes. So I think you will enjoy this session, and you can join with us. I'll share the link and you can also ask question by commenting. So sir, welcome again. It's time you can start your session.
Okay. Well, thank you very much for that kind introduction. I assume everyone can hear me. If you can't, or I cut out at any point, just let me know, because I can't see you, or even myself for that matter, on the screen. I can just see my slides. I don't know where you all are in the world, but right here it's in the USA, in the central time zone, it's 7 a.m. And so you'll start to see in the window over there the sun coming up. But it's okay. I like getting up early, so this is my prime time for speaking. So yeah, I want to talk today about planetesimal formation in circumstellar disks. So if you're not familiar with all of those or any of those terms, I'll define them as we go through the talk. But first, I just want to acknowledge my various collaborators. This work is certainly not done in a vacuum. It's not done just by me, but I benefit from a number of collaborators, including postdocs such as Urshan Lee at Cornell, Andrew Yoon at University of Arizona, Catherine Krecke at Southwest Research, where I spent a number of years, and a number of other people. Phil Armitage, I want to point out, because he was my postdoctoral advisor for many years and one of my closest colleagues. And I think he is the person that I have the most papers with as of right now, at least. That'll probably change as I start publishing more with other people. Oh, and I do definitely want to mention my research group. I have a postdoc, Daniel Carrera, who's been outstanding, and you'll see some of his work presented later in the talk. And then I have 3 graduate students: David Ray, Jianghong Lim, and Abigail Davenport, these two students are coming along quite nicely. They're more senior, and Abigail's still beginning, but she has a very strong potential future. And then I have an undergraduate researcher with me as well, who's learning the ropes, learning how to do computational simulations. Okay, so back to the science after acknowledging my group. So what are circumstellar disks? That was one of the phrases or one of the terms in my title. So circumstellar disks are disks of gas and dust orbiting around young stars. So stars that are not yet fully formed, they don't yet have nuclear fusion working in the cores of the stars. So they're called protostars. They've just collapsed and formed and are only lit up by the fact that they're sort of hot still from the collapse process. And then as part of this collapse of gas and dust, you get this sort of frisbee-like structure that forms. And this is the circumstellar disk. Now, how that actually happens, I don't want to go into that. That would take a long time to explain. But what I do want to point out is that these disks are the birthplaces for planetary systems. Planets form in these circumstellar disks. Whoops, I skipped ahead a little bit too much there. And as hopefully many of you are aware, but if not, that's fine. Planets are a big topic right now in research in astronomy. We are in the sort of golden era of trying to understand how planets form, and that's motivated largely by a lot of space missions such as the Kepler Space Telescope and now James Webb Space Telescope to try to characterize these exoplanets, planets around others. So my work ties into sort of the theory behind it and trying to understand how planets themselves form and get into the configurations that we observe them in. And so, yeah, planets form in these circumstellar disks. And the process by which this happens is outlined by this cartoon. Now, I do want to point out that this is a cartoon, and so there's a lot of physics that is sort of being brushed over here. But I just wanted to give you an overview of what's happening or what we think happens in planet formation. And I want to clarify that a number of these steps, right, has a lot of uncertainty with it still, and that's where some of my research comes into play. Okay, so like I said before, gas and dust orbit around a young star. I should also point out this is a cross-sectional view of the disk. So if we go to this and we sort of reorient the disk and take a meridional slice, that is what this is. So this is radius away from here. This is the star or the forming star. This is radius in that direction, and this is up and down, right? So this is the flat, and the disks tend to be flared like this too, but it's just a cartoon. And so this disk would actually extend over here as well, but this is just showing this this half for a more illustrative reason. But anyway, so gas and dust are in this sort of frisbee-like structure, this circumstellar disk. And over time, the dust settles out due to vertical gravity. So there's a vertical component of the star's gravity that pulls on everything. Now the gas is supported against that gravity due to the fact that it's hot. It has a thermal pressure, but the dust doesn't feel this. And so the dust settles out into a thinner layer, like another disk within the disk. And eventually that dust grows into into objects that are called planetesimals. I'll describe what that is in a minute. But then ultimately these planetesimals merge together or accrete remaining other dust grains that were left over in this stage, and they form planetary systems, or at least protoplanetary systems, where you might have large planetary embryos. Maybe that's more like this stage, and then into this stage, planetary embryos. These embryos continue to merge, and also the gas giants the planets that will become gas giants will accrete the remaining gas in the disk and form gas giants, and then you get something that looks maybe like our solar system, maybe not, because it turns out that exoplanet systems are very diverse, and many of them don't look even remotely like our solar system. This is the solar system just as a demonstration. So this kind of encapsulates the broad brush picture of planet formation. What I'm particularly interested in is planetesimal formation, this middle step here, which is where you go from dust grains to larger bodies. And this is a critical step in planetesimal formation. So But before I get into that, what are these planetesimals that I'm talking about? Well, simply put, they're asteroids. They're objects like asteroids, comets, or the distant Kuiper Belt objects. And there's a number of other planetesimal populations in the solar system. Basically, they're small, rocky and icy, not always icy, but rocky and or icy bodies, ranging in diameter from about 1 to a few hundred kilometers, this sort of scale here. And there's a number of populations in our solar system that are planetesimals. I already mentioned asteroids, right? There's the main asteroid belt that orbits at about 3 times the distance from the sun as the Earth does, and so that's between the orbits of Mars and Jupiter. There's also a population of Trojan asteroids that are in trapped in the orbit of Jupiter. And then there's other populations too, but I really want to point out, because it becomes relevant later in the talk, is the distant Kuiper Belt. The Kuiper Belt is a very distant, beyond the orbit of Pluto, beyond the orbit of Neptune, icy region, or sorry, a region where you have a bunch of icy planetesimals, right? So I also want to point out that, not only do we know these populations exist, we've actually visited them. I mean, not humans necessarily. No human has gone and stood on one of these objects, but we have sent missions out to visit these objects. In particular, the Rosetta mission, which was a number of years ago now, visited the comet 67P, and this is an actual image from that spacecraft, from the Rosetta mission. And it even sent a little lander, the Philae lander, to land on it. It wasn't the most successful lander. It bounced a lot when it landed, but we still got a lot of good data from this. And then more recently, there is the New Horizons spacecraft run out of the United States through a number of agencies, including NASA, where they've sent the first mission for New Horizons was to actually visit Pluto, but it kept going after it visited Pluto, and then it encountered another Kuiper Belt object, which is shown here. This is an actual observation. This is not a simulation. This is actual observations of New Horizons as it approaches and gets closer and thus more resolved image of Mu-69. That's the name of this object. Actually, now it's called Arrokoth, but I still gotta go by Mu-69 because that's what I learned about. Now, I do want to point out that there's a difference, even though this image is smaller, the Comet 67P is actually smaller. In this case, the sort of diameter, if you want to call it that, it's not quite a sphere, is about 4 kilometers. Whereas Mu-69, you have this sort of weird bilobate structure where you have two spheroids kind of just touching each other, and that's about 35 kilometers in length. So there's a range in sizes and properties, but a number of missions, even things that I haven't had a chance to talk about, are visiting these small bodies and trying to understand them. So why are we so interested in how these planetesimals form? Well, you may have gathered from a few slides ago that they were the intermediate step between small dust grains and fully grown planets, or at least planetary embryos, which are kind of just the step before fully grown planets. Well, planetesimal formation is very hard to understand and to get right for a number of reasons that I'll explain here. But also, it requires a very, very large scale increase over a short amount of time. So you start with micrometer size dust grains. The disk inherits that from the interstellar medium, and then those things stick together through like van der Waals forces, and ultimately become something like centimeter size little pebbles, right? Something that you can hold in your hand. I suppose you could hold the micron dust grain in your hand too, but then it'd blow away, right? But the little pebble, like gravel in your driveway or something you might find on the beach. And then somehow this has to get from this scale all the way up to 100 kilometer scales, and then to fully grown planets, right? The problem is that there are growth barriers between these two stages. So this is sort of a cartoon to represent that, but what are these growth barriers? Well, one in particular, and the only one I'm going to talk about for now, is something called the fragmentation and bouncing barrier, which I'm sort of using to mean the same thing, although they're slightly different. But basically what happens is when you have these pebbles and you try to stick them together, at some point their sticking fails and they either bounce apart or fragment. Now, this has been explored both theoretically but mostly experimentally. This is a drop tower in Bremen, Germany, where basically they take a canister of silicate particles or whatever particles they're trying to study, and they drop it from all the way up here to down there. And as they do that, microgravity, the conditions in space are simulated for a moment, right? Or that's technically not simulated; it's in free fall, so that's exactly what's happening, right? But so what they do then is they allow these bodies to collide with each other, and they determine how efficient the sticking is. In other words, do centimeter-sized objects stick together through something like van der Waals forces or material properties? And the answer is no. That's sort of the punchline from these numerous studies, and you can see Bloom and Worm, 2008, for reference. The punchline is that solids cannot stick together beyond millimeter to centimeter sizes, right? It's very difficult to do that. You might have some routes where in some cases there's a statistical fluke, and you might have some sticking, or there might be icy grains can stick a little bit better, and people are investigating that, but it's very difficult to do. And so these growth barriers are present largely because of that. Okay, so how do you get around that? What is the issue? We know that planetesimals form, and we know that dust grains exist and pebbles exist. So how do you get around that? Well, about, I don't know, 15 years ago now or so, a little bit less, an idea was put forth to explain this. And that is that there's a process in circumstellar disks called the streaming instability. I'll just refer to it as SI for short. But basically, this streaming instability arises from the exchange of angular momentum in the disk between gas and dust, right? The gas and dust are in the disk together, and they're aerodynamically coupled. And this aerodynamical coupling provides an instability to occur, which then, well, I'll show you what happens, right? Before we get into that, I just want to orient you to what several movies that I'm going to be showing shortly. This is something called the local shearing box approximation. So first, here's that cartoon disk again. Here's a cross-sectional view. And so this is the star. Sorry, this is not the disk. This is the star. This is the disk. And we just take a little chunk out of that disk and zoom in on it and put all of our computational resources to understanding the physics in this little box. Now, the reason we do that is that it's very computationally expensive to run the simulations of the whole disk at the resolutions necessary to understand the streaming instability. So I just wanted to orient you here. We're simulating a small co-rotating patch of the disk, and this direction corresponds to the azimuthal disk around, or azimuthal direction. We also call it toroidal. This is the radial direction, this way, sorry, not up. Radial direction is this way, away from the star, and vertical direction is up. So this is using the Athena code, which I helped do some of the development work on back as a PhD student. But now that I hope you're properly oriented, let me know if you're not, and I can go through it again, or you can talk to me afterwards. This is a tool that I use almost exclusively, although I do some other tools as well. But let's now flip this box and look down on the top. And in fact, we're just vertically integrating through the top of the box. And so this is now the azimuthal direction, and this is the radial direction. So that's towards the star. And this is basically what's called the surface density of particles. We basically just integrate the mass density of particles through the box vertically. And I'm showing the log of that relative to the background average, right? Oops, the wrong button. Okay, so we start with a uniform mixture of dust grains. And so most of it's like blue and yellow, which is just, sorry, blue and gray. and that means that this is unity, right? But over time, what you'll notice is that there's more and more yellow and more blue. These yellow regions are regions of higher concentration of pebbles, these little grains that I was talking about before. And the blue regions are where there's large voids of those. I hope that movie came across. I know it's being piped across the world, and this is, I apologize if it was a little bit chunky, right? Or what's the right word? Well, I hope it came across nicely. But you can always go to my webpage if you want to see nicer, more smooth versions of this movie, because I have a bunch of them on my website. Okay, so these regions here now, these regions are regions of larger numbers of pebbles, and this process is called the streaming instability, and it's sort of analogous to a peloton. If you're familiar with pelotons, like in the Tour de France or any number of other bicycle races, cyclists get into these configurations where they move together to reduce their mutual aerodynamic drag. It's also called drafting, right? So this person back here will feel much less headwind than this person up here. And so it's actually quite energetically favorable for pebbles to get into the same kind of configuration, and the streaming instability provides a route to do so. So you can kind of think of these as little pebble pelotons if you want. So, but what does that have to do with planetesimal formation? Well, let's take that same movie I just showed and sort of reorient it again. Actually, what's shown here in the blue and green down here is another simulation, but it's showing the same thing that I just showed in the movie. And then, so vertically integrated. Now this way is towards the star, that way is azimuthal, that way is vertical, and up here is the actual particles themselves, right? So at some point, there's so many pebbles concentrated in these filaments, these elongated filaments, that gravity takes over. So if I just play this, you can see now that gravitationally bound objects have formed. These are planetesimals. So the basic idea, right, is that you need a large number of pebbles in a small region. If you don't have that, then tidal forces from the sun try to rip things apart. But if you have enough of these pebbles concentrated, then they can gravitationally collapse. And the route to do that is simply the streaming instability producing enough of these little particle pelotons for this gravitational collapse to ensue. Okay, so the streaming instability is currently the leading candidate to sort of jump over these growth barriers, right? You don't actually have to stick millimeter, centimeter size pebbles together. You just avoid that altogether and just have them collapse gravitationally to this sort of planetesimal size scales. More pictorially, this is kind of what's happening, right? These pebbles, this is not at all to scale, by the way. These are centimeter sizes. This is 100 kilometer size. That's 1 kilometer. So just a cartoon. They gravitationally collapse, and then they form either large objects or small objects or some number of sizes in between. And they are not necessarily sticking together like smaller grains would be sticking to form pebbles. They are gravitationally attracted to each other. So they're sort of more loosely bound. They're not materially sticking together, not until they get really compact, at least. They do not collisionally stick. Okay, so I do want to point out that there's an alternative school of thought, and I just refer to it broadly here as the collisional model. It's not really a well-defined model because there's different people that do different aspects of it. But the basis of it is that the collisional model basically assumes that growth barriers can be surpassed, right? They sort of just ignore this. And the reason for that is, well, for one, they maybe just choose to ignore it for simplicity and say, something will work. But other people say, well, there are possible routes through this growth barrier. Maybe you have really, really fluffy grains and instead of compact grains like of this size or this size. And these grains are fluffy and not compact, so they might stick together more easily. Now, all of that is still very much not understood and being investigated, but it doesn't seem particularly likely to me. Nonetheless, it's still worth investigating in. So, I look forward to hearing more results of that. But for now, I just want to point out that the collisional model sort of assumes that there is a way to get past these growth barriers. And so the collisional model is simply that you actually start off with, you actually go from millimeter sizes, centimeter sizes, up to about 1 kilometer in size. So you transverse this large scale, right? About a 10 to the 5 factor increase here. In scale. And then once you get these 1 kilometer sized bodies, then they collide and gravitationally stick together to form even larger bodies, right? And you still have some small bodies left over, so you might get a range of sizes here as well. Now, this outline is sort of the outline for the rest of my talk. That was mostly introductory material. I'm not, this is not to say that a huge amount of talk is left, but I do want to go through these things because this now, with that introduction, is sort of that introduction sort of served as the background that you need to understand my research and how it comes into play with all of this. So there are several questions. And so not only is this an outline, but this is sort of a guide that we have done in my group and my collaborators to try to understand the properties of planetesimal formation. What we want to do basically is test the streaming instability as the mechanism for planetesimal formation. We showed in simulations that it can form planetesimals, but does it actually agree with what observations tell us, right? We can look at the distant Kuiper belt, for example, or the asteroid belt, and see what sort of properties those bodies have and compare them with our simulations. Okay, so let's just start with some basic results from the simulations, which are determining properties of planetesimals, and in particular, looking at the initial mass or equivalently size distribution. Let me get a drink of water real quick. It's very cold here, and that means it's also very dry. So my apologies for occasionally needing to get some water. So what we did with my collaborator, Urshan Lee, who I'm trying to recruit as a postdoc, by the way, he's excellent. Basically we looked at the mass and size distribution of these objects. And so this is just the mass function, the number of objects in the mass bin, where the mass is on this axis, and it's in this funny unit mg, which I don't want to explain where that comes from, but for reference, this is about 10 to the minus 4 masses of the moon. So this is very, very small, right? But this is actually the right sort of range that you would expect planetesimals to be in. What we showed is that you get this kind of shape, and oftentimes the most important aspect of the shape is that you get way more small bodies than large bodies, and in some cases you might even have kind of a turnover up here, although I think this still remains to be examined further, because in other simulations you see it keep going upwards. So most planetesimals are of small scales, but when you look at the mass distribution in terms of total masses in each bin, most of the mass is in the large bodies, right? So basically this is like integrating this with mass under the integral, right? The mass of each body. And so the largest planetesimals have the most mass, but there are more small planetesimals. This shape in particular is something I want you to keep in mind as we go further through the talk. But another thing that we can learn from these simulations is something called binaries, right? We see that a lot of these clumps, a lot of these planetesimals are spinning so rapidly that they become binary planetesimals. They actually sort of separate out. They kind of there's like a fission process, and they separate out and become binaries. And so we looked at the distribution of a number of things, of a number of properties of these planetesimal binaries. The first is, and the only one I'm going to present, is the binary inclination. So what this means is, how does the orbit of the binary compare to the orbit of the whole binary system around the sun, right? And so if it's prograde, so if binary inclination is less than 90 degrees, then the binaries, the two planetesimals, are orbiting each other in the same sense as they go around the sun. So their angular momentum vectors are aligned, and retrograde is the exact opposite. They're anti-aligned, right? Angular momentum vector here will be pointing down, but the angular momentum vector around the sun is pointing up using the right-hand rule, right? And so we found that about 80% of our binaries are prograde, or less than 90 degrees, whereas retrograde is only 2%, or sorry, 20%. There's other things that we looked at, like the actual angular momentum distribution, the angular momentum in this particular in these particular binaries, and they sort of show the same basic result as this. But now it comes the real meat of what we would do, which is testing the streaming instability model as the leading candidate for self-consistent growth from millimeter sizes to greater than kilometer sizes. So again, I want to point out that we're comparing with systems with our own solar system. Now, why not systems around other stars? Well, planetesimals are unfortunate in that they're way too small to be seen by direct imaging. Like, even though by looking at other solar systems, we can only really infer planets exist if they pass in front of their star, or if they tug gravitationally on the star, or if the planets themselves are so big that they light up, right? They're hot and we can see them. So we can detect planets around other stars. But planetesimals are so small that they don't really tug on the star very much, and they certainly won't do much to pass in front of the star, and they wouldn't produce much of a dip in the light, and they certainly aren't hot enough to be observed. And they're also too large to be to know. So we can actually see millimeter and centimeter grains in these disks, because those grains are warm and emitting, but we can't observe planetesimals in other circumstellar disks around other systems, or in other planetary systems, fully formed planetary systems. But my point is, we have to use our own solar system, and in particular, we use the distant Kuiper belt. And the reason for that is that the Kuiper belt is the most pristine population of planetesimals in the solar system. The asteroid belt, while it's much closer, has been collisionally evolved over time, and that sort of changes the properties of the planetesimals after they form. And what we want is a comparison of the planetesimals right after they form from the streaming instability with something as pristine as possible, and that is the Kuiper belt, because it's much less collisionally evolved. And so the population of planetesimals in the Kuiper belt represents the best comparison that we can do. Okay, so let's start where we ended before, which is with the binaries, right? So if you actually look at the observations now, this is the red line from a paper by my collaborator, Will Grundy, 2019. That's the red line. And our blue line is, as before, again, 80% prograde, 20% retrograde. And you can see there's agreement. Now, there's some fluctuations, but if you sort of sample the simulations to calculate an uncertainty, this gray area is basically a 1 sigma error, but not from the observations, rather from the statistical properties of the simulations. You do find that there is remarkable agreement between the two. Maybe not perfect agreement, but again, within the uncertainties, it's remarkable agreement. Now, the collisional model, for comparison, it's a little, well, okay, so there's two versions of the collisional model. The first is that you start off with high velocity Kuiper belt objects and collide them together to form larger bodies. Remember, this model assumes you start with kilometer-sized bodies and grow up to about 100-kilometer sizes. If you assume that and you do high velocities to start, then you actually get 50% prograde, 50% retrograde. That's this dot dash black line here. If you do low velocity collisions, only 3% are prograde. So you would have like a curve that sort of starts down here and goes up like that, right? So in this case, most of the planetesimals in the collisional model are retrograde. So clearly, this test rules out, at least currently, the current implementation, the current understanding of the collisional model, right? They either predict an even number of retrograde and prograde, or mostly retrograde, whereas we predict more prograde, and that definitely falls within the agreements with observations. So this was a very big win for the streaming instability, and I was pleased to be part of it. You can see our papers here. One is in Nature Astronomy, and one is in the Planetary Science Journal. This is sort of a follow-up to this. And I should also point out, just as a little shameless self-advertising, I recently wrote a Comets 3 chapter, or it's a book chapter on how planetesimals form in the Comets 3 book. Now, the book hasn't been published yet, but you can find this on archive on the AstroPH if you search for my name, or if you just look at my website, it should be under my publication list. But now here comes the rub, right? Here comes the issue. If we look at the size distribution, so this is similar to the mass distribution I showed before, but now we're showing the size and the number of objects greater than a given size. This is the cumulative size distribution. If you look at this, neither the collisional model nor the streaming instability model agree with observations. So what do I mean by observations? Well, this blue line here is informed by a recent paper by J.J. Cavallars in 2021, where they did probably the best job at fitting the observational data on the Kuiper belt with an actual model for what the size distribution is, and it sort of has this power law with an exponential tail as you get to large sizes. Now, there's always uncertainties in observations as well, but this is considered the current state of the art, right? So this is not observational data. This is a fit to observational data. But it doesn't really matter because the darn curves up here are so far off that it's clearly not in agreement. Also, I want to point out, if you're looking at this little box and wondering what these are, ST here is just the Stokes number, which is basically just related to the particle size, and Z here is the amount of material relative to the gas. So the particle surface density relative to the gas surface density. And this is the proportional to the particle size. So the green, orange, and red clearly have too many planetesimals, and their shapes don't really match, maybe. It's hard to tell because they're so offset. But the collisional model also doesn't really agree. Maybe it looks a little bit closer, but again, produces way too many planetesimals. And if you want to look at the collisional model, the most recent, I think, was 10 years ago now by Hilke Schlichting in 2013. She's a professor at the UCLA in Los Angeles in the US. Okay, so let's just rescale these curves to try to line them up and see if they work better. Well, if you do that, the collisional model does look a little bit better, but you still can't explain some of these features. If you were to go down here, if you were to extrapolate, it looks like it might go over here. It's a little bit better, right? Maybe that's okay. But the weird thing is when you rescale, this is just arbitrarily rescaled for each data set, right? We're not scaling all of the curves the same amount. You see that the green and orange at least match really well at the high end, although not at all at the low end for smaller size planetesimals. I don't know what to make of this. This was just something I decided to do for this book chapter that I've written, but it's interesting. Now the question is, right, what is going on here? Before I sort of explain what we think might be reasons for the discrepancy, I just want to say, sort of reiterate the key results so far. The streaming instability predicts results consistent with observations of binary properties, but neither the SI or the collisional model is consistent with observed size distributions. I'm going to get a drink of coffee here. I am a morning person, but coffee helps with that. And as you can see, the sun has currently risen. Okay, so to try to get around this size distribution issue, my group is working to further test the SI, but we're trying to improve not only the analysis of our simulation data, but also adding in more accurate physics, right? The way that, at least in my field, it works, you start with the simplest physics possible, and you compare that with observations to see, well, is that in agreement, or do we actually need to consider something else? You sort of build from there. Okay, so going to kind of the last part of my outline here is the improving tools and physics of the model, which is what I just said. And so there's kind of three branches to this. One was work that was partially carried out by my former master's student, Matt Small. He left last year with a master's degree from Iowa State. And then also my current graduate student and one of my past graduate students is looking at the influence of turbulence. I'll explain what that is in a minute. And then my postdoc and a former undergrad, we're looking at the formation of planetesimals in dust streams. I'll explain what all of these are. Let's start with clump tracking. So one thing that I've just brushed over so far is that these planetesimals aren't technically planetesimals. They are basically gravitationally bound objects, but because we have our gravity that provides the collapse is discretized on the grid scale of the grid, right? We're using a discretized representation of space and time, and these grid cells here represent space. The way we do gravity prevents these planetesimals from collapsing much below that, right? You can see this particular clump is just, it spans a few grid cells, right? So really what this is a giant particle cloud, and it's about 10 to the 4, 10 to the 5 times larger than planetesimals themselves, the actual planetesimals, right? So these are like 10 to the 5 kilometers at the minimum, right? That's just a limitation of our numerical simulations, unfortunately. There's ways around that, which I'll get to. I just want to point out, if you have questions about this, you can ask afterwards, or email me. This is a technical aside, so I don't want to spend too much time on it, but I wanted to point it out because it is a limitation. One way we can get around this is by extracting one of those clumps gravitationally and just put it into a better gravity solver. And this is what I've done with my collaborator, David Nizvorny. Basically, this is one of those things. This is a particle cloud, now gravitationally bound to itself, right? And it's extracted from one of these simulations and put into another code that handles gravity much better in a much more accurate way. And if you run this, you'll see, well, not surprisingly, collapse continues, but other things happen as well. So eventually, as collapse occurs, you get a rotating disk that forms, and that disk itself kind of breaks apart and flings out more material. Now, a lot of different things are going on, right? And over time, some of this material comes back and lands on the main one, the main clump here. But at the end of the day, you do get gravitationally bound planetesimals. They are smaller in size, but you also have lost some of the mass. Although, sorry, I shouldn't say that. You keep most of the mass, but you do sort of redistribute mass a little bit. Now, I didn't have the movie for this, but most simulations actually, when you run them longer, you end up with a binary, right? You do end up with a binary, like we predicted. You end up with a binary planetesimal. So one planetesimal orbiting another planetesimal, and they're roughly equal size bodies, right? So that's an agreement as well. And the reason we didn't have this for our 2019 paper, you can ask me about, and I'll tell you more details about that. But the point is, right, that it shows that we do get planetesimals form if you do a better gravity solver. And it shows that it doesn't necessarily stay all in one body. Most of you, or about, I think it's more like 50%. Sorry, 50% of the binary of the simulations did form binaries, and other ones form just one big planetesimal, right? So this is just to show that we can, in fact, form planetesimals and get around the issue that I showed before. But that's really expensive to do, right? So if you want to do one of these zoom-in calculations for every single planetesimal that's formed in one of these gas dynamic simulations, that would take a very, very long time. But another idea that was actually developed by my former graduate student, who's now in industry in the US, I forget which company he works for, he developed a way to keep track of each gravitationally bound clump as soon as they form, right? So basically, this is just, you don't have to understand this plot. Basically, it's just a logical diagram showing that certain clumps will merge, other clumps will split apart. But basically, the trick is that you keep track of all this and only look at the clumps once they form. And so you don't have any issues with like merging large, fluffy these large clumps that I talked about before that are not fully collapsed, you don't have any issue with them sort of gravitationally interacting and distorting each other. You're looking at the gravitationally bound clumps as soon as they form, and then keep track of that. So this is a better approximation to this initial mass function or the initial size distribution than would otherwise be, right? It's still not perfect. The perfect thing would be the perfect thing would actually be to have the a much higher resolution simulation, but that's just not computationally feasible. The next best thing would be zoom ins, but that's also not computationally feasible. So then we do this sort of workaround. And the reason why I mentioned this, right? This looking at zoom ins and all that, it's still important, but I want to point out that even just doing this better analysis of the mass function, where you just look at the masses once they form and then ignore them after that, so that you don't have to worry about, this basically means you don't have to worry about which snapshot in your simulation that you're looking at. It's a better representation of the mass function, right? So there is, if you look at the simulation, right, well, there's still discrepancy at small scales. I suspect this is a resolution, and if we did a high resolution, you get more and more small bodies, and so this is probably just resolution limit the code. But up here, where you can actually resolve the formation of a large number of planetesimals, the slope is quite similar, although not quite as accurate as that, as this, right? Or sorry, it's the slope looks similar, although it's not right on top of it, right? So this is encouraging, but more work is needed. Another thing I want to say about this is that n has been rescaled. So basically, normally this curve would be way up here. I've rescaled it on purpose to make it to see if it lines up with this, but it turns out that this other problem I talked about before still exists, right? So maybe this looking at a better treatment or better calculation, better analysis of the initial mass function is a way to solve this discrepancy in the shape of the mass function, but the fact that you had more planetesimals form than is observed is still an issue that we have to resolve, and we don't fully understand that. But that's where my next project comes into play, led by my graduate student Jing Hun Lim. So these simulations so far are just of a small patch of the disk. Now, in these circumstellar disks are actually thought to be quite turbulent. The gas is driven to be turbulent through, say, magnetic fields stirring up the gas. There's other possibility as well. So we don't know. We're sort of staying agnostic to this, and we're just injecting turbulence into our simulation domain with a given characteristic, right? A given amplitude. And this is to mimic what might be actually driving the turbulence that we may not be able to capture in our small domain because the domain size is too small. But it's also an advantage, right? We don't have to say anything about, we don't have to say, oh, magnetic fields are creating this turbulence or some other process. We just inject the turbulence using an algorithm and then study its effect on planetesimal formation, right? So this is a step towards more realistic simulations. And this is really the only slide on this. But the main takeaway I want you to get is that turbulence may in fact reduce the efficiency of planetesimal formation, but maybe not quench it altogether. So this plot just shows the maximum density of pebbles relative to the initial gas density over time. This is basically, if you go above this dotted line, you formed planetesimals. So the higher the value means the larger, the more filament structure that forms, and then more planetesimals form, right? But the point of this is that by doing different alpha here is the strength of turbulence relative to the gas pressure, right? That's what alpha is. And here's our parameters, that same as before. If you turn up alpha, you get weaker and weaker degrees of filament formation, right? So this is saying that if there's perhaps some moderate level of turbulence, oh, sorry, this is the control run. If there's some moderate level of turbulence here, it can reduce perhaps the number of planetesimals that form. You see, this doesn't quite get up here, but if we ran this long enough, it's very possible that this would go back up and you'd get occasional bursts of small numbers of planetesimals. But the point is, right, if you increase the turbulence, you decrease this sort of curve, which means you're more likely to only occasionally go above this dotted line and form planetesimals. This dotted line is something called the Roche density. Basically, it's the density at which gravity of the pebbles overpowers that tidal destructive force that I was talking about earlier. So again, turbulence will just reduce the efficiency of planetesimal formation. We don't know by how much. Zheng-Hun is still working on this, and in fact, he's trying to fix a bug in the code that was there for a long time. So hopefully, once he gets past that, I think he's pretty close. They'll be really able to hammer this down and determine whether turbulence can truly reduce the efficiency of the planetesimal formation, which is something we need to do in order to match observations. And finally, the last few minutes I want to talk about, I don't know how much time I have left, but this shouldn't take too long. The last bit of time, or the last thing I want to talk about, are planetesimals born in dust rings. So I don't know if you're familiar with the images like this, but I'm going to assume that you aren't. These are images of disks, circumstellar disks around different stars, and we're actually looking at millimeter to centimeter sized pebbles in these disks. We see these because they're hot and they're re-emitting their radiation at the right wavelength that we can observe them. And so what we see in most of these disks is that they have these ring structures, right? This was first discovered in 2014 around the system HL Tau, which is not shown here, but this is a follow-up looking at a number of disks, and all disks have some structure of some form. Some, this disk it's not as easy to see, but there is some structure there. So you have disks of varying, you have different types of structure, like you have thin rings, thicker rings, some cases even have more like spiral structures. But the point is, all of these circumstellar disks have axisymmetric dust rings or spirals of some kind. So why are we focusing on that? Well, the reason that these rings exist is likely that there is a local maximum in the gas pressure, or at least a change in the gas pressure gradient, right? This leads to pebbles being trapped there. Now, I don't have time to explain why that works, but basically, pebbles move towards regions of higher gas pressure. There's a angular momentum exchange that allows this to happen. If there is a local maximum in the gas pressure, such as in this cartoon, pebbles will move towards it and get trapped. The pebbles over here can continue over there, but any pebbles over here will move up to there and get trapped. Any pebbles that started here will go up to here and get trapped. But even if it's not a local maximum, changes in the slope of this could cause like a traffic jam effect where pebbles momentarily line up or get to a higher density. So these pressure bumps leads to dust enhancements, and that influences the streaming instability. Now, why is this important? Well, another thing about those simulations that I showed in the beginning of my talk is that we oftentimes just assumed that there was enough material to form to trigger the SI, when in fact you actually need a little bit higher dust to gas ratio to trigger the SI in the first place. To be more specific, if you look at the Z parameter here, Z is the ratio of basically the dust gas ratio. If it's above 0.02, then the streaming instability can be triggered. But that's not necessarily going to be the case in the circumstellar disks, because on average it's about 1%, right? So at 0.02 is the most optimistic case. It oftentimes needs to be higher. So these pressure bumps are a natural site for the enhancement or for the local change in Z and to kick off the streaming instability. And I just want to sort of highlight one major result from this work, which shows that if you start with centimeter-sized grains, you get planetesimals that form, right? These you can see now this is the vertical versus radial, this is azimuthal versus radial, and this is just a 1D thing showing the dust density. Here's the pressure bump around here, and as you see, as the material drifted into the pressure bump, planetesimals were born, right? And they were formed here. Now that's the case if you start with centimeter-sized grains, shown here also on this plot. But if you look with millimeter-sized grains, the story is different altogether. And millimeter-sized grains, I'll just point it out here. Millimeter-sized grains never trigger the streaming instability. They never get to a high enough density in these bumps to trigger the streaming instability. So what did we do? Well, we just made the bump stronger and stronger, and eventually we made a bump that trapped the pebbles, right? So we made the bump actually have a local maximum. And when you do that, planetesimals actually do form, but they don't form from the streaming instability, only from gravitational collapse. Basically, what's happening is that pebbles are just piling up, and eventually there's so much of them in that trap that planetesimals are born, not from the streaming instability, but just for being crammed into a small space, right? So why is this important? Well, this requires very large amplitude bumps, very strong bumps that lead to a pressure maximum. But these bumps may be unstable to secondary sort of instabilities, one called the Rossby wave instability. We don't yet know for sure if that's the case. If that's the case, then millimeter grains may not form planetesimals at all, which is a little bit of a worry because millimeter grains may be sort of where most of the mass is for small grains, because centimeter-sized grains, it's not clear how much of those actually exist in circumstellar disks. But if this isn't true, if indeed these disks are stable, or these bumps are stable, then millimeter-sized particles can form planetesimals, but perhaps not through the streaming instability, but just by direct collapse. And so this is another mechanism that we really want to understand further and compare with observations. So it's possible that these pressure bumps will actually produce fewer planetesimals. Like I showed in the movie before, you only saw a few forming. That's partially because it was a lower resolution simulation. If we did higher resolution, it's possible that these pressure bumps, sorry, I keep saying planetesimals when I mean pressure bumps. When these pressure bumps produce fewer planetesimals, we might then solve that planetesimal efficiency issue. But there are other things that we want to figure out. And, I've gone on long enough, so I don't want to take any more of your time. I just want to point out that there might be other workarounds around this millimeter size issue, but really the most important things are here on these sort of take-home points. And to reiterate, streaming instability is a potential route towards forming planetesimals. We find excellent agreement with solar system planetesimal binaries and tentative agreement in the shape size distribution when we looked at improved analysis tools, such as that initial mass function that I was working on with my previous student. And then preliminary work, though, suggests that turbulence may reduce the number of planetesimals. This is very preliminary. And pressure bumps also may reduce the efficiency, but we need to understand how this works with millimeter size grains versus centimeter size. It may not work for millimeter size grains at all. So with that, I will take any questions, and I thank you for your time.
Thank you, sir, for your excellent presentation.
No problem. Sure. Do I just stay in this mode for now?
Shubhankar, can you hear Shubhankar? If you have question, you can ask. So we have a question in the inbox. So how do the planetesimal form?
How do the planetesimals form? Was that the question?
Yes.
Okay, so the planetesimals form simply by let me go back, way back. Okay, so the streaming instability leads to these filaments, right? These filaments are regions where you have like small pebble size, centimeter size or millimeter size pebbles concentrated into very narrow regions. And when those regions are so dense, the gravity of those, the gravity between the pebbles themselves is enough to cause collapse, right? And normally, if they weren't that close together, this shear that you see, which is the result of the Keplerian shear, will try to disrupt it, right? Try to tear it apart. But the streaming instability allows there to be such strongly concentrated pebbles that the gravity wins at the end of the day, and you get something that forms gravitationally bound planetesimals. As I said before, these are actually fluffy particle clouds, but when we actually look closer with better gravity simulations, we do find that planetesimals still form.
So
I hope
can
that,
this, yeah,
yeah.
there is another question similar. So can this planetesimal form planet like our Earth later?
Yeah. In fact, we do believe that planetesimals turn into planets in the most general sense. And the way that happens is that these planetesimals can, after this stage is done, they might merge with each other. We can't track that in our simulations again because of the fact that these are very diffuse particle clouds and our gravity solver isn't good enough. But if we were to do that, we would find that planetesimals could merge together, or they would just accrete up these smaller dust grains and pebbles that are left over and form Earth or other planets. And I want to point out that the asteroid belt is basically a failed planet. The asteroid belt would have done this, but Jupiter's massive gravity prevented it from ever forming a planet. And same with the Kuiper belt. Neptune prevented the Kuiper belt from turning into planets. So the Kuiper belt and the asteroid belt are basically failed planets. And it's good for us so that we can have a thing to compare with.
Sir, thank you. This may be the last question. So is it possible to find living being other planet like what we're in Earth in our galaxy or
So
other galaxy?
yeah, certainly not in other galaxies right now. So one of the main things that we're trying to do in my field is to determine if the conditions for life might exist in other solar systems. One way you can do that is not so much my work, but we can colleagues of mine look at how the chemistry of these disks work, and so they look for signatures of carbon or oxygen, right? These are like, if you've taken organic chemistry or chemistry of that type, you know that these are the building blocks of life. And so if we know where the carbon is and maybe the water is as well, we can look for potential signs of life. Another way is this James Webb Space Telescope that launched last year and has been taking spectacular images. It's looking at the atmospheres of distant exoplanets and looking for signatures of life there. As far as like reaching toward other intelligent beings, I think that's a long way off. There is the SETI program, Search for Extraterrestrial Intelligence, that's still been going on, but that's a whole other area. It's not in my expertise, so I don't want to say too much about it because I don't want to mess up. I don't want to get anything wrong.
Okay, thank you, sir. So this may be the last question for me. Actually, if any of my student and the student from Bangladesh, because here everybody study the physics in graduate and undergraduate student, they are mostly. So what they need to do if they want to pursue their career in astrophysics and astronomy, like?
So what if they're bachelor students, you said?
Yeah, no, after bachelor in physics, can they go in astronomy directly, or they need to do some extra course there for PhD or masters?
There are certainly ways to. I mean, a lot of the students at Iowa State, for example, come in here with no astronomy background, but then they start working in astronomy. So it's certainly not a requirement that if you have only a physics degree and no astronomy knowledge, that you have to have that to go to graduate school. So, the way to do that, if you have a physics degree, come to a graduate school that will probably be maybe a mix of physics and astronomy, and or maybe other departments like astronomy departments, and you have a strong physics background, they may hire you or bring you on as a graduate student, and then you'll take classes there, and you'll also learn from your PhD advisor all of the astronomy that you really need to know. And you'll learn more and more astronomy as time goes on, because you'll attend colloquia, you'll attend webinars like this one,
Yes.
you'll just gradually get more and more information.
Yeah, I found that you have also completed your bachelor in physics and then completed your master's in astronomy. Okay,
Yeah,
so
I did have a minor in astronomy. So like, I don't know if you know what that means. It's basically, I took astronomy classes at University of Illinois, but my degree was physics, right? That's where
okay,
I did most of my work. Yeah.
okay. So thank you, sir, for giving us this opportunity. I think it's a great opportunity for a student and the viewers to interact with you directly.
Okay,
So
thanks.
thanks again, and hopefully in near future we can arrange another webinar with you.
Yeah,
On a
I'd
very interesting topic.
I'd be happy to do that.
Okay.
And if anybody has any more questions, you can
Yeah, I
feel
can.
free to
Yeah.
email me. My email address is on my website. You can just type my name, and then you should be able to find me. So
Yeah, thank you, sir.
thank
See
you.
you. Have a nice day.
Bye-bye.
Bye-bye.